Muy buenas tardes a todos. Bienvenidos a esta última plenaria del 15º Congreso Nacional del Congreso de la Sociedad Matemática Mexicana. ¡Ay, sí, 50! Bueno, el 50 con un cerito Congreso de la Sociedad. Gracias, Javier. Gracias, maestro. Bueno, es para mí un honor enorme y un gran placer presentar a la última conferencista plenaria, que es la doctora Angela Pistoia. Angela trabaja en la Universidad de Roma, La Sapienza, y es experta en ecuaciones diferenciales parciales no lineales. Angela es italiana, nació en la Toscana y estudió tanto la licenciatura como el doctorado en la Universidad de Pisa. Y poco después de que terminó el doctorado, le ofrecieron una chamba en Roma, entonces se fue a trabajar a Roma y allí en ecuaciones diferenciales parciales no lineales, particularmente usando métodos variacionales y métodos de reducción finita. Además, trabaja en problemas de análisis geométrico, como el que nos va a platicar hoy, que se refiere al problema de Yamabe. Angela es una persona que pues es de las personas más destacadas en esta área. Ella tiene a la fecha 130 artículos publicados con alrededor de 1,300 citas, pero además es una persona muy creativa y muy generosa. Yo creo que casi todos los que trabajamos en esta área hemos trabajado con Angela porque trabaja con todo el mundo y de veras es un grandísimo placer trabajar con ella. Es de veras una persona creativa, generosa y particularmente con los jóvenes. Ella ha trabajado, por ejemplo, ha recibido en Roma a mis estudiantes de doctorado y siempre regresan de allá muy motivados y muy entusiasmados. Déjenme decirles también que como persona es una persona estupenda. Tiene una familia preciosa, su marido, Massimo Grossi, también es un matemático muy destacado, tiene 2 hijos guapísimos y es una mamá estupenda. Se interesa también mucho por las cuestiones de género, entonces ha sido promotora de la igualdad de género y ha sido vicepresidente de la Asociación de Mujeres Europeas en Matemáticas. Ya no les digo más, dejo a Angela con ustedes. Grazie mille, Angela.
Okay. Let me thank Monica for this wonderful opening. I'm sorry because my English is not good. My Spanish is zero at all. But I am very, very honored to be here. And it is a pleasure for me to be in this wonderful campus. In Italy, we don't have a campus like this. I have to be honest. This is fantastic. And also the atmosphere is very good. I usually spend 1 week, at least 1 week every day to work with Monica in this wonderful place. So thank you for this. I am conmossa. I don't know how to say in Spanish conmossa, but conmovida. Okay, I'm conmovida. Okay, let's talk about mathematics. Okay. Okay, so I will speak about this topic, and I will talk about. Let me introduce the problem using a very important problem, which is famous, is the Poincaré conjecture. Okay, the starting point of my talk is the Poincaré conjecture. And before Poincaré conjecture is conjecture, there was this uniformization theorem which says that every simply connected closed surface is homomorphic to the 2 spheres. Okay? So if I have a surface and the surface is such that any path can be deformed to a point, then this surface is a 2-sphere. This conjecture was completely proved by Poincaré and Kerb at the beginning of the last century. Okay? One of the ingredients of the proof was that any metric any metric, is it always possible to find a metric which is conformal equivalent to the one I have on the surface, for which the Gaussian curvature is constant? Okay, this was done at the beginning of the last century. After this theorem was proved, Poincaré says that the same is true for the three-dimensional manifolds. More precisely, what it says was the following. Every simply connected closed three-manifold is homomorphic to a three-sphere. Okay, this conjecture was proved a few years ago by Grigori Perelman in 3 papers, which are not published, but they are free in arXiv. Okay, so the conjecture now is completely solved. But before Grigori Perelman solved the conjecture, Yamabe, in 1960, tried to prove the conjecture. And he wanted to follow the same idea, follow it when people studied the uniformization theorem. So what he wanted to prove was the following, that if I have a closed M-Riemannian manifold without a compact M-Riemannian manifold without boundary, then it is always possible to find a metric which is conformally equivalent to the one I have on the manifold, for which the scalar curvature is constant. The scalar curvature in higher dimension, in 2 dimensions, is the same of the Gaussian curvature. So this was his project, and they claimed and he proved this fact. But 8 years later, Trödinger found a gap in the proof. The proof was not correct, and so this gives rise to one of the most important problems in the linear analysis of manifold, the so-called Yamabe problem. What is the Yamabe problem? The Yamabe problem is the following. Let us take a manifold without boundary, compact manifold. Is it possible to find a metric conformally equivalent to the one I have on the manifold, for which the scalar curvature is constant? This is the Yamabe problem. And this is, in my opinion, this is very beautiful because this purely geometric problem can be reformulated into a partial differential equation settings. So finding a metric is equivalent in some sense to finding a solution to an equation. Let me tell you how we can do this, okay? Okay, before to give you the equation, I need to introduce some stuff, some geometric stuff, some curvature tensors, okay? So what I do, I take this compact Riemannian manifold and I introduce the curvature tensor, which is given by this, for this green formula. This formula here. This is a 4 tensor, okay? If I take the trace of this tensor and I contract 2 indices in this way, what I get is the Ricci curvature tensor. Okay, this is a 2 tensor. Then what I do, I take the trace of this Ricci curvature tensor, and what again I get is the scalar curvature. Okay, if m is equal to, the scalar curvature is nothing but the Gaussian curvature. Okay, twice the Gaussian curvature. And it is important to point out that for the round sphere, I mean the sphere with the usual, the standard metric, then the Ricci tensor, the Ricci tensor here is a multiple of the metric, and the scalar curvature is a constant, is m times n minus 1, where m is the dimension of the manifold, of the sphere. Okay, this is one ingredient, and now let me give you the PD formulation. So I have this metric G. I take the conformal class of the metric, this guy here. Sorry, but I have some problem with the... Okay, this is... I cannot see very well, sorry. I cannot use this guy. Okay, so the conformal class of G is a positive multiple of the metric G. The metric is positive. I take the metric, multiply by phi, I get another metric. This is a conformal class because this guy here preserves the angles. Okay? This is important. And now what I do, I take a conformal metric, which I write like G tilde equal to U to the power 4 over n minus 2 times G. I write the conformal factor in this strange way, U to the capital 4 over minus 2. U is a positive function, okay? This is a conformal factor, and what I do, I compute the scalar curvature of this new metric in terms of the scalar curvature of the initial metric G, and in terms of the conformal factor U. And what I get this green relation, you see that. In the bracket, I have an operator, which is an elliptic operator. Delta G is the Laplace operator, the Laplace-Beltrami operator associated with the metric, the Laplacian. If I have in the Euclidean case, this is nothing but the Laplacian. And the minus something which is linear with a coefficient which is this guy, which depends on Rg. And this is the quantity into the bracket is the conformal Laplacian. This is conformal because if I change the metric, it changes in a good way. Okay? This is what I have. And now you see that if the Yamabe problem says the following. I want to change the metric in the conformal way so that the scalar curvature related to the new metric is constant. So you see that Rg tilde is constant, means that I put this guy on the other side, I can solve this problem. So you see that if I'm looking for a metric whose scalar curvature is constant, what I do is the following. I look for a strictly positive solution to this equation on the manifold. Okay? So now, in order to solve the Yamabe problem, I will look for positive solution to these partial differential equations on the manifold. Lg is like the Laplacian, okay? Is a second order elliptic operator. So now let me tell you, so we have an equation. How can we solve this equation? We can use the variational structure of the problem. I mean, there is an energy, this pink energy on the, you see here, which is on the numerator, we have this integral, which depends on the gradient. The derivative of the upper side, let me say, is the conformal Laplacian, in some sense. The denominator there is the nonlinearity on the left-hand side. Okay. So we have this energy. Critical points of this energy are a solution to the problem, but it is important to introduce a quotient, which is the infimum of J on the space H1G. This function, this energy, acts on this space H1G, which is a Sobolev space. It contains the function whose derivatives exist, more or less. What I do, I take the infimum of J on this space, and it is clear that because of the Sobolev embedding of H1 into LP, this embedding is continuous, so the infimum exists. But now the exponent 2m over n minus 2 is the critical exponent because the embedding is continuous, but it is not compact. So the infimum cannot be achieved. Okay, that's the problem, because I don't have the compactness. So the infimum cannot be a minimum. And that's a problem, because if the Yamabe quotient is achieved, the minimum is a solution to the equation, so I get a solution to the Yamabe problem. Okay, this is the story. So what I want to do is to find a critical problem, and to find a critical point of J. What I want to do is to prove that the Yamabe quotient is achieved. So it is a minimum. This is the point. And this simple question is extremely difficult to to answer, because let us see what happens. Let us consider the standard case, which is the case of the sphere, the Euclidean sphere. Okay, let me say in this way. Let us consider the round sphere. And in that case, the Yamabe quotient is achieved. But unfortunately, it is achieved by too many functions. Indeed, what I can prove is the following. Let me write the equation on the sphere, which is the first line there. This is the first equation on the sphere. I want to read the equation on the sphere on the Euclidean space. I use the stereographic projection, which is a conformal transformation. And what I get is this famous equation in the Euclidean space. This equation in the Euclidean space has infinitely many solutions because, first of all, if you have a solution and you translate, you get another solution. So there is an invariance by translation. But there is also another invariance, which is due to the dilation here, you see. So the problem has infinitely many solutions, which are called standard bubbles. These are important because they are the main ingredients in solving the Yamabe problem and also in this talk. Which is the shape of these bubbles? These are the following. There is this blue function here, which is radially symmetric. It achieves the maximum at the origin. And then what you get is the following. You translate the maximum at another point, and then you make a dilation. As this parameter delta is going to 0, the solution is going to 0 everywhere, except at the point y, where it achieves the maximum, and at the maximum it goes to plus infinity. So the bubbles looks like this way. The bubbles is going to 0 everywhere, except at the maximum point where it blows up at plus infinity. Okay, this is the picture. Okay, this is the bubble in the Euclidean space, and if you come back to the sphere using the stereographic projection, you get something like this. Okay. So the Yamabe quotient on the sphere is achieved, but there are too many functions which achieves. And that's a problem because if I want to solve the Yamabe problem, I have to be sure that I cannot find so many solutions because otherwise there is a lack of compactness. I cannot deal with this infimum. And indeed, what Aubin in 1976 proved was this wonderful result. It says that if the Yamabe quotient is strictly less than the quotient on the sphere, then the Yamabe quotient is achieved and the Yamabe problem is solved. Okay, so to solve the Yamabe problem, it is sufficient to find the test function whose energy is below to this guy, to the Yamabe quotient on the sphere. That's the point, to find a good function. And finding a good function took a lot of time, at least 20 years, more or less. Let me tell you why. Okay, there are three cases. One is the green case here, when the Yamabe quotient is less or equal than 0. This is, let me say, easier. It was solved by Trüdinger and Aubin many years ago. It was the first result. The second result is when the Yamabe quotient is positive, but the manifold is not locally conformally flat, and the dimension of the manifold is greater or equal than 6. Not locally conformally, a manifold which is locally conformally flat, it looks like very close to the point, is conformally equivalent to the Euclidean space. That's the idea, to the sphere, okay? And finally, the most difficult case is when the Yamabe quotient is positive and the manifold is locally conformally flat and all the dimension is 3, 4, 5. And it took a lot of time because as you see here, it was solved in 1984 under an assumption which involves the positive mass theorem, and I will be back to this problem in a few minutes, or in a different way by reusing the critical points at infinity. Okay, here you see the people who gave the most important the proof of the most important part. Okay, so let me tell you how to build this test function, because it will be useful to describe what I did with some of my collaborators. Okay, but in any case, let me tell you. First of all, the wild tensor. Let me introduce the wild tensor. The wild tensor looks like a mess, because you see this is a tensor, which is the trace-free part of the Riemann tensor. The definition is terrible. And also it involves, you see, the Riemann tensor. This is the Schouten tensor, so it's a mess. But if I want to tell you what the wild tensor measures, I can tell you the following. The curvature tensors gives you some information about how much the volume of the balls is different from the volume of the Euclidean balls. This is what the curvature measures. The wild tensors give you the information about how the shape of the manifold is different from the Euclidean setting. Let me tell you in this way. But what it is important is that the wild tensor is conformally invariant. I mean, if I change the metric of the manifold in the conformal way, the scalar curvature changes, but the wild tensor, no. So this is very intrinsic of the problem. And let me also tell you that if m is equal 3, the wild tensor identically vanishes, so it doesn't carry any information. But if m is greater or equal than 4, the wild curvature tensor vanishes if and only if the manifold is locally conformally flat. Okay, this is what happens. And the second, so one ingredient in order to solve the Yamabe problem is the wild tensor. The second ingredient is the Green's function. The Green's function can be defined in this way. I have this conformal Laplacian. Assume that it is positive. Think about the Laplacian, okay? Okay, if I want to solve the problem minus LG minus conformal Laplacian equal to a Dirac delta at a point C0 on the manifold, then what I get is a Green function, the so-called Green function, okay? And what it is possible to prove, Lee and Parker proved the following fact. If I am in low dimension, 3, 4, 5, or the manifold is locally conformally flat, I can write the Green's function around the point xi0 like a singular part, which is this one. It blows up as the point x goes to the point xi0, plus this red term. This red term plays a crucial role in the studying of Yamabe problem. This m xi0 is called the mass of the operator. And this is smooth, this is a smooth function, and it was supposed to be strictly positive. This is the famous positive mass conjecture, which was proved in low dimension by Lee and Parker, Schoen, Yau, and Witten. It was also proved in the case of the locally conformally flat case, but only this here, or the last here, it was proved in the general situation by Lockham. So the positive mass is strictly positive. And now we are ready to solve the Yamabe problem, because you see, remember that to solve the Yamabe problem, I need to find the test function whose energy is less than the energy, the Yamabe quotient on the sphere. And what I take is the bubble. You see, I take the bubble. This is the Euclidean bubble. I read the bubble on the manifold. This is the tangent space. Okay, I make this. So I take the bubble in Rm. I read the bubble on the tangent plane at the manifold, and I compute the energy. Now, this is too rough, and the good test function is more elaborated. More or less, this is the idea. And what I get is the following. I computed the energy, and the energy, I remember that my bubble is concentrating, so the delta parameter is going to 0. The first term of the energy is the Yamabe quotient of the sphere minus something. In the three cases, I have the mu0, which is the bad level. I have to be strictly below this bad level in order to get a solution. So I have this bad level minus something, the green guys here. And all these three guys are strictly negative. You see that when the dimension is low, or when the Wald tensor is 0, we have the mass. In the other case, we have to work with the Wald tensor. Okay, this is more or less the idea. So the Yamabe problem was solved, and so the problem now, the second step is how many solutions does it have? So is it unique, the solution, or not? Okay, if the Yamabe quotient in the negative case, in the case of negative scalar curvature, the solution is unique. There is only one solution. If this is 0, if the Yamabe quotient is 0, the solution is unique up to translation, up to a constant factor. And the most difficult case, the most interesting case, is when the Yamabe quotient is strictly positive. Indeed, in that case, the solution is not unique. Schoen and Pollack, when they built examples of examples of manifolds which are like tori, this way, for which there exists a large number of solutions, was Morse index goes to plus infinity. So as many solutions as we want. So it is natural to ask what are the properties of the full set of solutions to the Yamabe problem. And in particular, Schoen conjectured that the set of solutions is compact. This was the famous Schoen conjecture. It is compact unless the manifold is the sphere, because in the sphere there are infinitely many solutions, and the set of solutions is not compact because of this blowing up procedure. Okay, and again, the geometric problem can be formulated into a PDE framework. Indeed, using the Harnack inequalities and the standard elliptic estimates, the compactness is equivalent to establish a priori estimates to the solution to the PDE. So the set of metric is compact. In the positive case, I can assume that the scalar curvature is 1. Is compact if and only if the set of solution to the PDE is a compact set. So there are no blowing up solutions for this equation. Compact means that I cannot find solution was L infinity norm is going to plus infinity. So this is the problem. This was conjectured by Schoen, and the results are the following. The Yamabe quotient is compact when the dimension is between 3 and 24. There is this number, strange number 24, but this is sharp because Brendel and Marquez proved that when the dimension is greater or equal than 25, the problem is not compact anymore. Indeed, what they did was the following. They took the sphere, and they built a metric on the sphere, which is not locally conformally flat, for which the problem has a family of solutions which blows up at one point on the sphere. This is what they did. Okay, these are the final step. You see, the conjecture was Schoen conjecture, the claim in 1988, and it took about 20 years to prove the conjecture. It was very hard, and there are many results in between. Okay, but finally, it is completed. And which is the ingredient of the proof? The ingredient of the proof of the compactness relies on proving sharp pointwise estimates at the blowout point of the solution. The problem is not compact. It means that there is a family of solutions which blows up at one point. What does it mean that it blows up at one point? There is a point of the manifold for which the solution, okay, let me tell you better. I say that Xi0 is a blow-up point for the family of solution if there is a point Xn where Un achieves the maximum, for which the maximum value goes to plus infinity, and the maximum point approaches the point Xi0. This is the definition of blow-up point. And the compactness result relies on the fact that all the possible blow-up points are isolated and simple. What does it mean? It means that if I look at the solution close to the blow-up point, what I see is exactly the standard bubble, the Euclidean standard bubble. This is what it can be proved, what the people proved. What is an isolated and simple blow-up point? Now, here I have a slide with the definition. They are too complicated. Let me give you the picture because it is easier in my opinion. So you see, in the last picture, you see Xi0, this red point is a blow-up point, so the solution is going to plus infinity at that point. It is isolated and simple. It means that the solution looks like one bubble, only one bubble. The point is isolated but not simple. What does it mean? It means that the solution has one maximum point, but if you look at the solution, you don't see a bubble, but you see a superposition of bubbles. You have one bubble, then above you have another bubble, like a tower. This is a towering blow-up point. It is isolated, it has a maximum, but the problem is that there are two bubbles. And finally, the blow-up point can be also not isolated. What does it mean? It means that the solution close to the point looks like two bubbles which are collapsing to the same point. This is the clustering phenomena. Well, the first two phenomena cannot happen when the Yamabe problem is compact. This is strictly forbidden. Only the third case can happen. Okay? This is the story. So, existence of Yamabe problem is clear. The compactness is clear. Now, what can we do to understand if the Yamabe problem is stable or not? What is this stability property? Roughly speaking, is the following. I take the Yamabe equation, I shake the Yamabe equation, perturbing the Yamabe equation in some way. Do I produce, using this shaking, solutions which blow up or not? Does it mean that if we slightly perturb the Yamabe equation, do we create solutions which stand far from a solution to the initial Yamabe equation? This is the problem. Okay, let me give you some more precise definition. And I say that the Yamabe equation is stable if for any sequence, for any H1 bounded sequence of the equation, here you see if epsilon is 0, this is nothing but the Yamabe equation. So I perturb, I shake, introducing this linear perturbation. And the problem is stable if, given this sequence, there exists a solution U0 such that U epsilon converges to U0. You see that if the Yamabe problem is stable, the blow-up phenomena are strictly forbidden because a solution which blows up at one or more point does not satisfy this equation because they blows up. Then L infinity norm is going to plus infinity. And so the question one can ask is the Yamabe problem stable? And the answers are the following. When m is equal 3, the Yamabe problem is stable. This is proved by Li and Zhou and Drouet some years ago. And when m is greater or equal than 4, the Yamabe equation is not stable. It's not stable because we can prove that there exists a family of solutions which blows up at one point of the manifold as epsilon goes to 0. Blowing up means that the solution is going to plus infinity. Okay, and what it is interesting, what I think it is interesting is that the blow-up points are never isolated nor simple. If the dimension of the manifold is greater or equal than 7 and the manifold is not locally conformally flat. Indeed, we can build solutions whose blow-up point looks like a clustering and solutions whose blow-up point looks like a tower. Okay, so cluster means bubbles which accumulated. Towers means one bubble over the other. And that's interesting because in the Euclidean case, this is strictly forbidden. All the blow-up points are isolated and simple. So the geometry gives you a richness in the existence of solutions. This is the point. The Euclidean space is too poor. In order to find a solution, you have to work with manifolds with rich geometry. This is more or less the idea. Okay, let me give you the right statement, and the rest, the right statements, they look like this one. Okay, assume, how much, at 6:30 I have to finish? See, I think so. Oh, maybe, see, okay. So, let me give you the statement of the results. Assume that, you remember that if I want to solve the Yamabe problem, I have to make a difference between the case of low dimension, the case of the locally conformally flat case, and the case of not locally conformally. So, in the same spirit, there are two different situations. The situation where the wild tensor plays a role, and the situation where the mass of the manifold plays a role. Okay? And in both cases, if I have a critical point, a good critical point of the wild tensor or a good critical point of the mass, I can find a solution which blows up at that point. Okay? This is the statement. And moreover, if this point is good, I mean, let us consider the case where the manifold is not locally conformally flat and the dimension is greater or equal than 7, then I know that critical points of the wild tensors gives you solutions which blows up at that point. Well, if that point is good, I mean, for example, it is a non-degenerate minimum point, what I can find that this blow-up point is a clustering blow-up point. What does it mean? You see in the picture, I can build as many solutions as you want. Peaks was blowing up point collapse to the same point. This is a cluster phenomenon. And moreover, if the manifold is symmetric with respect to the point xi naught, where the wild tensor is different from 0, then xi0 is also a towering point. What does it mean? It means that I can build a solution with as many peaks as you want, which looks like a superposition of bubbles. Okay, this is what it can be done. And the picture, you see the picture of the towering. Okay, now the results are finished. Let me make some remarks on the assumption because they are interesting. One can say, okay, but do there exist manifolds for which this kind of assumption are true, or are you cheating? No, okay. First of all, let us consider the case of the critical points of the norm of the wild tensor. The wild tensor is the 4 tensors. I take the norm of this 4 tensor, make the square. I take a critical point of this function at a level different from 0. Well, it is possible to prove. I need a non-degenerate critical point of this guy. Okay, it is possible to prove that for most matrix G, the critical points are non-degenerate. It is like a Morse function. Okay, and indeed, to prove this theorem, we use Sartre's lemma. Okay, something like this, transversality argument. So, okay, the set of metrics for which the wild tensor is a Morse function is not empty. And moreover, I also need a manifold for which the minimum of the wild tensor is not 0. And what I have to do is to take the product of around the sphere. The sphere is such that the wild tensor is 0 because the sphere is locally conformally flat. But the product of sphere is not. And the wild tensor is different from 0 at any point. Okay, the second group of assumption concerns the case of symmetric manifolds. What is a symmetric manifold? Symmetric manifold is a manifold such that you look at the tangent space. Okay, the tangent space is such that there is an isometry on the manifold for which the differential of the derivative of this isometry read on the tangent space is minus the identity. The sphere is symmetric with respect to any point. But the sphere is not good because the wild tensor vanishes, so what I have to take is the product of the spheres, the tori. The tori are such that the wild tensor is different from 0 at any point, and the tori are symmetric with respect to any point. Okay, so our set of assumptions is not empty. And let me give you an idea of the proof, just an idea, because I would like to talk to you about this Lyapunov-Schmidt procedure. This Lyapunov-Schmidt procedure is very trendy, is very cool, because it allows to prove a lot of things, in particular that the George's conjecture was proved using this refinement, not this one, but a refinement of the Lyapunov-Schmidt procedure. So let me give you just an idea of the proof, because this is very technical. What is the finite dimensional Lyapunov-Schmidt reduction? It's the following. There are 3 steps to use the Lyapunov-Schmidt procedure. The first one, remember that I want to build a solution, what to build by hands, okay? Yeah. So what I do, first of all, is to find a good approximation. Since we are playing with the bubbles is more or less a good approximation. The second step is to reduce the problem to a finite dimensional one, because this is very roughly speaking. The solution you are looking for belongs to a space of functions. The space of functions has infinite dimension. So what I want to do is to reduce the dimension from infinity to what? N plus 1, as you will see in one moment. To a finite dimensional space. And finally, once I have reduced the problem, I want to find the solution of the reduced problem. This is the procedure. It's very easy to say. Let me give you just a very brief idea about the proof when the dimension of the manifold is greater or equal than 7, and the manifold is not locally conformally flat. Remember that in this case, the wild tensors plays a role. This is the case. Okay, first step, to look for an approximated solution. Okay, this is more or less clear. I played up to now with bubbles, so what I want to do is the following. I take the manifold. I take a point of the manifold. I don't choose the point. I take just one point. I take the tangent space at that point. The tangent space is an Euclidean space of dimension m. So this is like Rm. On Rm, I take the bubble, okay? And via the exponential map in geodesic coordinate, I read the bubble on the manifold. This is what I do. The bubble, so as the maximum at the point C I have chosen on the manifold, and I am concentrating the bubble, so there is also this parameter delta. Delta is going to 0, the bubble is concentrating. So the solution is this V epsilon, I build in this way. There is an epsilon in the question, remember. Plus this green term. This green term is the remainder term. This is a lower order term. Okay, this is my answer. More or less, you see from the construction that what I want to find, is delta, concentration parameter, point psi. So more or less we are done, because I have to find n plus 1 things. 2 things. One delta and 1 point on the manifold which is like an Rm. Okay. This is the approximation. Now let us see how can we reduce the problem. First of all, usually this green guy here is the most difficult part, to find the error phi in terms of the delta and xi, of the 2 parameters. And another point, which is technical, but not, you can imagine that it is true, is that U epsilon, which looks like the bubble plus this lower order term, is a solution to my problem if, namely, a critical point of the energy, the problem has a variational structure, so the solutions are a critical point of something, if and only if the pair delta psi is a critical point of the reduced energy. The phi, the lower order term, depends on these 2 points, delta psi. And so it is clear that if I want a solution, I have to find the critical point of this I tilde. Okay? So, first step, the last step, is to look at the reduced problem. I have to compute the reduced energy because I have to find the critical point of this guy. And we can make the computation. What we see is that the reduced energy looks like mu0. Mu0 is the Yamabe quotient on the sphere, okay? Plus something, which is this blue part, which contains the concentration parameter delta and the Weyl tensor, plus higher order term. So, in order to find the critical point of this guy, what I have to do is to find the critical point of delta, which is the main part of the expansion. You see, sorry, this is the part which comes from Yamabe. And there is this epsilon part which comes from the perturbation. And finally, you see that this reduced energy has a critical point because the blue function has a maximum. As a maximum, because, for example, I take xi0, minimum point of the Weyl tensor with the level different from 0, then I maximize in psi, and I minimize in delta. And what I get is the critical point of phi. Then, since I tilde is very close to, I find the critical point, I find the critical point of f. Now, I tilde is very close to f. What I get is the critical point of I tilde. And that's all. This is very a concentrate of the Lyapunov-Schmidt procedure. So, let me thank you. Muchas gracias.
Okay, so are there questions?
So I have 2 questions. When you mentioned the stability property, it seems more natural to move the conformal class of the metric. So in the space of all metrics, in the manifold, you have the ones which are conformally equivalent to each one, and so you have like some kind of vibration. And it seems natural, instead of considering this perturbation that you made, one could think of making a general perturbation of the conformal class.
Yes.
That's one question. And the other question would be, it seems that the emphasis is on the bubbles and not on the homology of the manifold. They don't enter. So in some sense, is this related to the injectivity radius, in the sense that if the homology of the manifold is sufficiently small, perhaps it might get mixed with the bubbles? I don't see why the bubbles, if the homology of the manifold is very small, it might get mixed up with the bubbles and then produce some problem, but it seems from your exposition that that doesn't happen, so I wonder why.
No, you're right. both the questions are very interesting. The first question, I have to be honest, we thought about that. But we were not able to see how the Laplace-Beltrami operator depends on the perturbation of the metric. Maybe there are a lot of computation to do. That's the problem. Because you are thinking to a G, you perturb G like G plus epsilon H, and you need to see how the equation becomes. So maybe something can be done. We thought about that. And the second question is too difficult. I mean, we never, because I'm not an expert of homology. I think that you are right, something can be done. But I never thought about that. Because my geometry is a poor geometry, so sorry.
Any other question?
I guess the question is related to the previous one, in the sense that is it possible to obtain, in terms of the topology, let's say the homology of the manifold, bounds for the clustering phenomena, or how bad that is?
Okay, the construction I perform is a local, very local. I don't see the whole geometry. If I would like to see the whole geometry, I would use something different.
But in the sense, I mean, might be related to Barry and Coron's old result?
Exactly. Exactly. Barry tried to prove the Yamabe, to find the solution of the Yamabe problem following that point of view. Use the homology of the manifold. Here, the point of view is very local. Okay. It's very local. Even in the solution found by Schoen, you see, you need to prove that your Yamabe quotient is strictly below to the Yamabe quotient on the sphere. And to prove that, you find a solution which is concentrating around the point. So it is very local.
And if I may ask one last question. Have you thought about the parabolic problem, so the Yamabe flow?
This is what I would like to do. Indeed, there is a colleague of mine in Roma, and we are trying to work on the Yamabe flow, because you see, the first step, here we use epsilon as a parameter. But in the Yamabe flow, there is this natural parameter, which is the time.
Which is time, yeah.
Exactly. Mm-hmm. And I know that Del Pino and Wei and their colleagues are working on that, because the idea more or less, it's more complicated, but the idea more or less is this one, using the time to produce a solution.
Okay, thank you.
Any other question? Well, if not, let us thank... no, I have to do something, just a moment. I have to give something to Angela. Le tengo que dar una cosita a Angela que me encargó la sociedad que le diera. Entonces, paciencia, chamacos. Angela, so on behalf of the Mexican Mathematical Society, I want to thank you very much for this wonderful talk, and this is something that
thank you.
That's they are giving you.
A wonderful present. Okay, just one word. Let me tell you that I was very emotionata to give this talk, because I gave a lot of talk around the world, but in my opinion, this is one of the most I would say the most important one. So thank you very much for having to be here, to inviting me. Thank you.